Good afternoon, everybody. We'll just start in maybe 2 minutes. Let us wait for some other people to join. Actually, we are screening this live in the YouTube also, because we had an overwhelming response. We had about 733, registrations. So we'll just take 2 more minutes and then we start. So the speaker is ready, and I think, Amjad, are you ready?
Yes, I'm ready.
Okay, great.
Ma'am, before you just start, could you please give me a yes so that I can start the YouTube live here?
Sure.
Okay, that's great. Thank you.
Okay. We are 38, so I think we should start, or wait.
Yeah, it's time now.
It's time now, yeah, because okay, otherwise it's late for the we'll cut down on the question answers.
Before you start,
okay, everybody, thanks. Yeah, so we start on Linto. We just start in a minute, so you can just start. Yeah.
Okay, fine.
Sharing.
Thank you. Yeah.
Done.
Sarah.
Okay. Good afternoon, everybody, and everybody who's linked here on this virtual platform of the AOQR ECR webinar. I am Vinita Fartiyal, and I'm a quaternary researcher working at Birbal Sahni Institute of Paleosciences, Lucknow. And I'm the secretary of this Association of Quaternary Researchers, AOQR, that we call it. AOQR was a dream of many quaternary researchers in India, and since long, for working hand in hand under one single group and amalgamating a large pool of workers involved in quaternary research under a single frame of an association or a scientific group was much needed here in the Indian subcontinent. Our seniors have been talking about this since long. I remember in 2007 at the 17th INQA meetings in Cairns, Queensland, Australia, where Professor A.K. Singhvi mentioned how important it is to have an association, a national association in India. And this INQA meeting was also important because out of the several points that were discussed there, included the term quaternary, which was under the intense debate for several years. And there it was approved as a period. And simultaneously, the debate there began about the base of the quaternary, which was then set at 1.8 million years, but widely accepted as being 2.6 million years. So this was debated, and later in 2009, the quaternary was announced as the youngest period of Cenozoic era, with the base at 2.588 million years. So it was stamped by the International Commission on Stratigraphy there. Since then, we've met in several of the, in conferences and workshops. And I've always heard Professor Singhvi mention about this association. In 2017, in Vigyan Bhavan, during the 9th International Conference on Geomorphology in 2017, and then again in early last year in Goa in 2019, and then finally it was on the in Dublin during the 20th INQA in Ireland. In Dublin, lots of quaternary researchers from India participated. We were around 60. And there, in a meeting of the Indian delegates under the headship of Professor Singhvi, it was decided now that it's time to form a national association. And some of the young researchers, they volunteered to, for the newsletter. So we came back, we started towards this remarkable new association at BSIP with the support of the director, Birbal Sahni Institute of Radio Sciences, Dr. Vanna Prasad, and full support from the governing body, the research advisory committee, and the entire quaternary group of BSIP. So finally the day arrived, 12th December 2019, when AOQR was registered as a national association under the Societies Act 1860, with its headquarters at BSIP Lucknow. So 12th December is our Founders Day, and hence the beginning was made. And this beginning involves the hard work of many members of the Indian scientific community and all the 10 founder members of this association. So AOQR is committed towards the overall ascent of quaternary research in India and in the Indian subcontinent. And we all know that our subcontinent is unique. It's unique in its setting, it's unique in its geology, it's unique in its populace. It encompasses a full rainbow of quaternary climate, tectonics, surface processes ranging from the collision mountains to the third pole region to the rain shadow zone, then its foreland, the shield, the river system, cold and hot arid desert to a long coastline. So, and the network of the river systems here have been a witness to numerous social, agricultural, and anthropological events from prehistory to modern. So it is the cradle of civilization and has a long recorded history. So this unique, this unique subcontinent with so much of diversity offers a variety of archives to study different landforms, processes, neotectonics, human-climate interaction, resource management, and sustainable development. Moreover, since many decades, Indian researchers are known for their contributions in various aspects of quaternary studies and are recognized globally. We have had a galaxy, excuse me, we've had a galaxy of stalwarts in Indian quaternary. To name some, Professor S.S. Meher, Professor S.N. Rajguru, Professor I.B. Singh, Professor S.K. Tandon, Dr. A.K. Singhvi, Dr. R.P. Dheer, Dr. Amol Kar, Professor R. Ramesh, Professor Vishwas Kale, Dr. Chaya Sharma, Dr. Rajiv Nigam, Dr. N. Kumaran, Professor B.S. Kotlia, Professor L.S. Chamyal, Professor A.D. Singh, Professor Hima Chutan, Dr. R.R. Yadav, Dr. Amla Bhattacharya, Professor Sheila Dikshit, Dr. Sunil Singh, Professor Savinder Singh, Professor Sunil Day, Dr. Naveen Jiyal, Professor A.L. Ramanathan, Professor N. Janardhan Raju, Dr. Anupma Krishnamurthy, Dr. Shanti Pappu, Dr. Anjum Farooqi, Professor S.J. Sangore, Professor Subir Bera, Dr. Pradeep Srivastava, Dr. Rajiv Sinha, and the list could go on. And there are stalwarts like Professor K.S. Waldia who excel across all time scales. So we have this great, pool of acumen that's here in quaternary researchers. India is also blessed to have an enormous wealth of educational institutions, organizations, universities dedicated to science research, scientific research, and teaching. We have 9 IITs, we have 7 ISERs, we have 49 central universities, 367 state universities, 282 private universities, 123 deemed to be universities, 94 institutions of national importance, and 500 plus autonomous research institutes. We have 38 research laboratories under CSIR, 18 under DST. So the involvement of these several educational institutions and research organizations has developed the field of Indian quaternary studies manifold and taking it up to global standard and repute. So the continued effort of quaternary researchers reveal the extensive wealth of information and the knowledge hidden under the quaternary strata of the Indian subcontinent. These groups working in different pockets of the region exchanged ideas and opinions through various platforms, but coming together as one single group encompassing a diversified aspect of quaternary research will begin now. They were like the pearls spread over, which needed to be roped in one thread, and that is what AOQR aims at, to accomplish bringing all together as one fraternity, a stronger and impactful group. So AOQR has several plans to host several meetings, workshops, national field workshops, national conferences time and again. However, due to the lockdown, we could not just take off as we had planned, but surely we have some very good plans. The newsletter Quaternary Chronicles, which is an initiative of our young ECR team, is reaching you regularly in a scheduled time, ever since its conceptualization during the INQUA 2019. And we are planning a training on quaternary palynology this November, December. Please stay connected via this platform. We need you as much as you need us. Perhaps we need you more. I request you all to please become a part of our general body council by becoming members. There is an annual fee to it. It's nominal. For students, it's still less. And these contributions can help us immensely to plan the future workshops, awards, meetings, discussion forums all over India, and later publications too. So till date, the funds that we have are only from the generous contributions of the founder members, who have been helping at every step right from the beginning, contributing both their valuable time and their funds too. So please join AOQR as a member. Very soon we will have a website. It is in the final stages. It will be launched soon, and it will also have a payment gateway option, and the transactions will be very easy then. With these words about the association and its activities and plans, I welcome all of you on behalf of the President, Dr. Vanna Prasad, our office bearers, our founder members, our honorary members, and our dynamic ECR team to this webinar. Every Monday at 2:30 p.m., we meet for the next 2 months. Participation certificate will be provided to students and researchers who need it, and only if they attend all the talks. So, and then we'll send you a feedback form after this talk, and you are requested to please fill it and send it back to us on the same day of the talk. And for the students, it will be considered as an attendance also. So this time we are airing this webinar from Christ College, Thrissur, Kerala, due to some unavoidable circumstances at BSIP. I would like to thank the principal, Dr. Jolly Andrews, and Dr. Linto Alcott for their magnanimity and arranging this all in the last moment and doing it so well. So now today's talk is by Dr. Amjad Hussain Laskar from Geoscience Division of Physical Research Laboratory, India. It is my pleasure to introduce the young speaker of today. So Dr. Amjad Hussain Laskar did his MSc in Physics from Indian Institute of Technology, Guwahati, India, and his PhD in Physics from Physical Research Laboratory, Ahmedabad. He was a postdoctoral fellow at the Academia Sinica, Taiwan during 2013 to 2017, and a Mary Skolotska Curie Fellow at the Utrecht University, Netherlands during 2017 to 2019. Presently, he's a reader at the Geoscience Division of the PRL, Ahmedabad, and his main research interests include traditional and non-traditional isotope geochemistry, paleoclimate reconstruction, geochronology, isotope hydrology, global carbon cycle, and atmospheric photochemistry. His achievements are: he got the Best Research Scholar Award at the 14th Indian Society for Mass Spectrometry Symposium cum Workshop in Kerala in 2011. And then, as I told you, he is an Academia Sinica postdoctoral fellow, he got in Taiwan 2013, and a Mary Skolotska Curie Individual Fellowship in 2017. I invite Dr. Laskar to deliver his talk on the paleoclimatic reconstruction using stable isotope in natural archives. Just one more thing before we listen to our speaker of today. Please type your questions and queries, if any, in the chat box. Our volunteers will put them together for the speaker to answer at the end. And we'll try to take as many questions as we can. But if they're still left, we will try to answer them from our website platform or the YouTube platform. So please do not worry on that. This is a forum to bring out the best of ordinary researchers and the best of research findings, and to link all of us together to find answers and to all the queries for a better understanding and a better deliverable. Thank you so much. Over to you, Amjad.
Am I audible? Can you confirm, am I audible?
Yes, Amjad.
Okay. Okay. Thank you. Thank you, Dr. Vinita Potyal, for your nice words, and I am very happy to know all these things, whatever you have done. And I would like to thank Association of Quaternary Researchers for inviting me for this talk, as well as giving me an opportunity to present some of the research works. Okay, so I will start sharing my screen now onward. Please let me know if my screen is visible.
Yes, Amjad, it's visible.
Okay, thank you.
Could you please make it a full screen?
Yeah, it's full screen now. Is it full screen?
Not yet.
But it is full screen in my screen.
Just show for slideshow. Could you go for slideshow?
Okay, maybe I can do it again. Is it full screen now?
No.
Not yet.
I don't know.
Just that slideshow button. If you show it, I think it should.
Yeah, slideshow. I press the slideshow, and it is full screen now on my screen.
All right.
If you have a screen extension, you have to go to the single display, and then you have to display that. If it is an extension,
Yes.
then it will.
It is full screen?
No, sorry, Amjad. If your computer is hooked up to a big monitor, then it won't show others the full screen. So you have to hook up directly the laptop. You have to remove the extension.
Okay. Let me do that. Sorry, we're presenting. Stop. Okay, I'm presenting again. I am sharing the entire screen. Is my screen visible now?
Yes, Amjad.
Now showing the full screen?
Yeah, it's good.
Yes, it is.
Okay. Thank you. Good afternoon to all of you. The title of my presentation is Paleoclimate Reconstruction Using Stable Isotopes in Natural Archives. Okay, so it is basically the applications of stable isotopes to understand the past climate. Okay. The outline of my talk will be like this. I will first briefly introduce, then what are the importance of paleoclimate studies. Okay, so what are the archives available and what are the proxies available for paleoclimate studies. Then I will apply those traditional and non-traditional isotopes for paleoclimate reconstruction. Okay, so I will explain what are these traditional and non-traditional isotopes, and finally I will summarize. Okay, so first, what is climate? This is for mostly for the beginners. So climate is the average daily weather for an extended period of time, say for 30 years in a certain location. Okay, so weather is different than climate. It is actually the state of the atmosphere with respect to wind, temperature, humidity, cloudiness and pressure in a short-term scale, minute, hours, day to day. Okay, so in one word, climate is what we expect at any time based on our experience, and weather is what happens actually. Okay, so there is a difference between climate and weather. Okay. Then what are the causes of this climate change? There are natural as well as man-made causes. Okay, so the natural causes of climate change are these changes to the Earth's orbital parameters. You know, this Earth orbit is not a circle; it is slightly elliptic. So eccentricity changes, obliquity changes, precision also changes, and this volcanic activity and all these things, etc. They are natural phenomena which cause the climate change. And what is the anthropogenic? What is human-made effect that can cause the climate change? Mainly fossil fuel burning, deforestation, use of fertilizers, cement production, and land use change. These are the man-made. So most important is the fossil fuel burning. Okay, so since the industrial revolution, okay, approximately 250 years ago, human activities contributed substantially to climate change, mostly by adding CO2 and other greenhouse gases to the atmosphere. So the increased greenhouse gases caused increase in the Earth's surface temperature, and that is called global warming. Okay, so here in this slide, I showed the concentration of the three major greenhouse gases: carbon monoxide, carbon dioxide, nitrous oxide, and methane for the last 2000 years. Okay, so you can see that for the most of these 2000 years, this concentration of these three greenhouse gases are more or less constant. Up to say 19th century, end of 19th century, it was more or less constant. There was not significant increase. But since the end of the 19th century, there is a drastic increase in all these three greenhouse gases, and that caused the warming. Okay, so here I have shown you the rise in temperature, Earth's temperature since 1960. Compared to the average temperature observed during 1850 to 1900. Okay, so you can see there is a rise of temperature by almost 0.7, 0.8 degree since 1960 to 2020. And if this trend continues, we will cross 1.5 degree in this target. Okay, so what is 1.5 degree target and 2 degree target? I will tell you. Okay, so in around 2040. So in 2040, if the temperature rises at this level, the Earth's average temperature will be 1.5 degree higher compared to that it was in 1850 to 1900. Okay, so there are various model scenarios here shown here. Okay, so 1.5 degree and 2 degree targets are actually the target sets in various this climate summit. For example, in the 2015 Paris Agreement, where the nations agreed to set the limit, that is the rise of temperature should not exceed 2 degree, and everybody agreed to set it is well below, and if possible at 1.5 degree. Okay, so here various scenarios are shown. Okay, so if these are based on the emissions of CO2 in the atmosphere, mainly CO2. Okay, so if actually the net increase of the CO2 stops, if there is no net increase of the CO2 after 2040 or after 2055, then these are the expected rise in temperatures. Okay, so this the middle one, this gray envelope, showing the rise in temperature. Okay, if there is a total seize of CO2, extra anthropogenic CO2 in the atmosphere after 2055. Okay, so if the this CO2, anthropogenic CO2 stops emitting in 2040, then this is the blue envelope. You can see this is the envelope. So if we can reduce the temperature, or you can reduce the rise of the CO2, total this emission of the CO2 by 2055, then probably we can achieve this 1.5 degree this temperature target. Okay, so if and along with that, some non-CO2 radiative forcings are also there. Okay, so if this non-CO2 radiative forcings also decreases, it is shown here, and if there is no control on this non-CO2 radiative forcing, then this is the top envelope. This is the this purple one. Okay, so all these scenarios are explained here in this slide. Actually, when there is no net CO2 emission after 2055 and 2040, Okay, and cumulative CO2 in the atmosphere if it goes to a constant level after 2055 or 2040, and non-CO2 radiative forcing, that is methane, nitrous oxide, and all these things, atmospheric water vapor, if they also start decreasing after 2040 or 2055. So these are the three scenarios which are shown here with these three envelopes. Okay. Now the question arises, is the recent rise in Earth's temperature is unique or similar temperature change happened in the past? So this is the one important question. If so, if there was a rise in Earth's temperature in the past as well, why and what rate Earth's temperature changed in the past? Why it changed and at what rate? So is there anything unique in the present rise of the CO2? Okay, so that can be answered if we can reconstruct Earth's past climate. Okay. So there are various paleoclimate archives. I have listed some major paleoclimate archives here. Ice core, because this ice deposits layer by layer. Every year one layer deposits. So if you can drill ice core and study the isotope from the deeper cores, then we can reconstruct past climatic conditions, because isotopes in those ice cores, both in the form of ice as well as bubbles trapped inside, they record the past climatic conditions. Similarly, tree rings form one rings for every year. So each ring records the isotopic composition of that particular year. So if we go from outer surface to the inner axis of the tree, we can go back in time and reconstruct past climate. We have corals. These are also calcium carbonate deposits in the ocean, mostly in shallow regions, and that can be used as paleoclimate archive. We have terrestrial archives such as Speleothems. They are calcium carbonates deposited in caves in crushed regions. So they also actually record the past climatic conditions in their isotopes. Okay, and the foraminifera in sediments, so ocean sediments, they also actually deposit layer by layer. And if we can recover some core from the ocean and measure the isotopic composition in the tiny calcium carbonate shells, which are called foraminifera, we can reconstruct past climatic conditions. Okay. The isotope proxies I will discuss today. Two isotope proxies. One is oxygen isotopic composition, and second one is clamped isotopic composition, that is clamped isotope paleothermometry. First one is traditional isotope, second one is non-traditional isotope. Okay, so I will limit my discussion today on these two isotopic proxies. There are many more isotope proxies, but I cannot discuss all of them due to time limitations. So I will only restrict myself on these two isotope proxies. Okay, so here I given in this slide, I have written this CO2, carbon dioxide molecule. Okay, so carbon has both carbon and oxygen isotopes, and oxygen actually has three stable isotopes: oxygen 16, oxygen 17, oxygen 18, and carbon has two stable isotopes: carbon 12 and 13. Okay, so a normal CO2 molecule is oxygen 16, carbon 12, and oxygen 16. It is the most abundant, more than 99%. Okay. Now, if we replace any of these isotopes, for example, if we replace carbon isotope carbon 12 by carbon 13, it is shown here, the top of the middle panel. If you replace one of the oxygen, say oxygen 18, oxygen 16 by oxygen 18, it is shown in the middle one. And if you replace one of the oxygen by oxygen 17, it is shown in the bottom one. Okay. So now the ratio between this, say for example, this middle one, 18O 12C16O divided by 16O 12C16O is the oxygen 18 ratio. Okay, similarly, if we replace two of these isotopes with the rare isotopes or more than two, that is called clamped isotope. In this, for example, in the last right side, oxygen 18 is replaced by oxygen 16 is replaced by oxygen 18, carbon is replaced by carbon 13. So two of these isotopes are replaced by the rare ones. So this is called doubly substituted or clamped isotopes. Abundance of this, speciality of this is that it purely depends on carbonate precipitation temperature or CO2 formation temperature. So now to define these two isotope proxies, first one is this: we express the oxygen isotopic composition by delta 18O. Okay, so delta 18O is the 18 by 16 ratio in sample divided by 18 by 16 in standard. then we subtract 1, and so it is basically the deviation of the 18/16 ratio in the sample compared to some standard. So this clumped isotope is defined by delta 47 in CO2. It is the ratio between the 47 CO2 by 44 CO2 in the sample, and if we have some CO2 in which all the isotopes are randomly distributed. That is explained on the right side. Okay, so that is the R47 is 47 CO2 by 44 CO2 ratio. So what is random? In this right side, actually, I have shown this oxygen molecule. Okay, so oxygen can be 16-16 or 16-18 or can be 18-18 also. Okay, so at the high temperature, actually most of the oxygen molecule will be oxygen 16-16 or 16-18. There will be very, very less chance of clumping of 18-18 molecule. Okay, so that is called isotopic ordering. But if you go to low temperature, you will see some of the oxygen 18 clumped. So here oxygen 18 is shown by dark red and 16 is shown by.
I have a request. Amjad, please stop. I think someone has gone to a presentation mode and your slides are completely gone.
Oh, sorry.
I think someone has gone into someone else from the audience has gone into presentation mode. Please let him come out.
Yeah.
Yeah. Could you please pin your presentation then so that it will be visible to everyone?
I think there is some problem.
Oh, okay. Okay. One. Okay. Let me stop and start presenting again.
I think
no, Amjad, I think you can click on your.
Arif
Start fertile. Sorry.
Dr. Arif Hussain, I think he has gone into presentation mode and that has created some problem probably.
Oh,
is it visible now, my screen?
Yes, yes.
Okay,
Yeah,
maybe I can.
You just pin your.
So I missed some slides.
No, your presentation is not visible. Your slides are not visible.
Now my slides are not visible?
Yes.
No, sir, they are visible, but you have to check it in the chat window. You have to pin that particular slide.
You just start the presentation mode again and come to that slide directly.
Okay, let me do that.
And I'm requesting all the other members to please unmute their microphone and also switch off the videos, because that will create problem during presentation, because just to improve the internet quality.
Yes, my
I
screen.
think Manoj is right. I request everybody to please mute yourself and also switch off your video mode so that Amjad can present and without any obstacle in between.
Now it is visible, Amjad. You can go ahead. Just make it full screen.
Okay, thank you. Is it visible still?
Yes, please.
Yes, no, that's fine.
Okay, so I just was explaining what is this delta 18 proxy and delta 47 proxy. So delta 47 is nothing but clumping of the heavier isotopes. So in this slide, actually right side, if you see, oxygen molecule is shown. So 16 is the pink and 18 is dark red. So in the high temperature, if you see very less 18 clumping, but if you go to lower temperature, you can see the 18 clumping significant. So that is called isotopic ordering. It is also called isotopic ordering. So I will discuss some of the applications of this clumped isotopes today. Okay, so first let me start with this I-score. The oxygen isotopic composition in the I-score is one of the best climate record. As I mentioned, this I-score deposits, ice layers deposit year by year. So if we can drill some I-score from polar regions, we can go back in time. Okay, so before that, let me tell you this temperature and the CO2 in the Earth's this Earth atmosphere in the past, and that is also this reconstructed from I-score. That is reconstructed from Epica Dome Sea I-score from Antarctica. Okay, so you can see that this CO2 in the past also increased and temperature also increased in the past. I mentioned that this recent rise in the Earth's temperature was unique. Now it is not unique. There was high temperature periods in the Earth in the past as well. So these you can see that the this last 800,000 CO2 and temperature records from the Antarctica. Okay, so there are events, there are periods where temperature and CO2 were very high. Okay, so were significantly high. Okay, so another important thing is that the CO2 and temperature, they go hand in hand. Okay, so either this temperature cause CO2 emission or CO2 cause temperature rise. Okay, so I'm not going to that debate today, but I just want to show you that this Earth's temperature was higher in the past as well, and CO2 also high. So what is unique in this recent rise in the temperature or recent rise in CO2? Again, here I show the CO2 concentration in the Earth's atmosphere in last 800,000 years. You can see Earth's atmosphere never had CO2 concentration higher than 300 parts per million. You can see in the left side, the scale is shown. But in the recent times, there is a sharp increase in the CO2 concentration in the Earth's atmosphere. Okay, so in 2016, it crossed 400 ppm level. So now it is 410 ppm. Okay, so now using oxygen isotopes, we can reconstruct the past temperature. How? It is explained here. Okay, so it is delta 18 is shown on the y-axis left side, and air temperature is shown on the top x-axis. Okay, so delta okay, so this is the relation between delta 18 and temperature observed in the Greenland. Okay, at present. So this is the principle of reconstruction of the temperature using delta 18O, and it is shown here. For last 140,000 years, that is the one full glacial cycle, okay, including this Holocene, is shown here, and that is derived from delta 18O from Epica Domsey ice core from Antarctica. Okay, so this you can see that this during the last glacial maxima about 20,000 years before, the temperature was in the polar regions was 10 degrees less compared to the present. And in the past also, you can see that this temperature was even higher than the present temperature. Okay, but the point is that the CO2 rise was never, the CO2 level was never that high. And even if you stop the CO2, as I showed in one previous slide, that even if you stop the CO2 by 2040 or 2055, still there will be rise in the temperature. Okay. So next I will discuss about the some reconstruction of the paleoclimate using oxygen isotopes in speleothems. So speleothems, as I mentioned, they are calcium carbonates deposited in caves in the karst regions. Okay. So what speleothems actually records? They record the oxygen isotope position in speleothem, records the oxygen isotope in rainfall. So we actually did a study from a cave named Baratang, that is in Andaman Islands, shown in the left top map. Okay, so Baratang is shown here. Okay, so we recovered some speleothems from this Baratang cave and did oxygen isotope study. So the speleothems which I studied here are shown on the right top figure A and B. There are two speleothem samples we analyzed for oxygen isotopes, and this we dated using radiocarbon as well as uranium thorium dates. The dates are shown on the left bottom. Okay, so the smaller piece covers an age from 0 to 1000 years roughly, and the bigger piece covers an age from 1000 to 4000 years, that is calibrated. And as I mentioned, this oxygen isotopes in the speleothems, they record the oxygen isotope of rainfall. Okay, and it was observed that the rainfall delta 18 depends on two factors. One is mean monthly rainfall, that is called amount effect, that is in the most of the coastal and island stations. Of course, exceptions are there. And in the high latitude regions, it was observed that this delta 18 in the rainfall, they record the temperature. Actually, they vary depending on temperature. But in this case, we observed that this delta 18O depends on mean monthly rainfall. Okay, so then mean monthly rainfall actually, this is called amount effect, delta 18O in the Speleothem records the amount effect, and that is nothing but the monsoon strength. Okay, so here is the record of this delta 18O for last 4,000 years observed from the Speleothem from Baratang Island. Okay, so you can see that around 2000 years I have shaded some regions, some periods. Okay, 1500 I have shaded some. So what I mentioned, I told you in the previous slide that this oxygen isotopes in the rainfall, they respond to amount of rainfall. So when the amount of rainfall is less, oxygen isotopes is high. Okay, so if we follow that analogy, that is around 2000 years, the oxygen isotope was significantly higher compared to the other periods. And that period is reported as Roman I period. Okay, so in Europe, it was observed, it is very prominent, but it is observed in the Indian monsoon as well. Okay, so it is shown that this oxygen isotope responded very well, and there was a significant decrease in the monsoon strength. Okay, and another thing is that this in the medieval I period, around 1000 years before, we observed strengthening of the monsoon. And overall, there is a strengthening of the monsoon after 2000 years BP, before present. Okay, so, and it was, the present monsoon was established somewhere around 1000 years ago. Okay, so not only that, we compared this record with some other records from the nearby regions. In the top left, I have shown some black dots where some other studies are available. Okay, so this is, for example, this panel B is showing the log of varp thickness which observed from the northern Arabian Sea. So varp thickness, higher is the thickness means monsoon is stronger, lower the thickness of the varps, monsoon is warmer. So you observe the similar effect in the varp thickness, as well as the oxygen isotopic composition in some foraminifera in the nearby regions. Okay, and oxygen isotopes in some other speleothems in some coastal region in India. Okay. Then I will discuss about the paleoclimate reconstruction using oxygen isotopic composition in sediments. Okay, so sediments, mostly I mean ocean sediments. Sediments can be lake sediments as well. So sediments also deposits layer by layer, and the tiny, particularly in the ocean, this tiny calcium carbonate shells called foraminifera, they can be used to reconstruct past climatic conditions. And it is shown here. This is the longest oxygen isotopic record obtained from deep sea sediments, and it covers the last 65 million years. Okay, so you can see that this oxygen isotopes substantially buried in the past. Okay, and those variations are related to various climatic, tectonic, or even biotic events. Similarly, the carbon isotopic composition also varied, but I did not show the carbon isotope here. So an important thing I would like to tell you that this sea before 35 million years, the ocean was ice free. There was no ice in the polar regions. So this Antarctic ice started around 35 million years, and this Arctic started very recently. Okay, so before this ice formation, or when the ocean was ice free, we can use delta 18O to reconstruct the temperature. Okay, so ocean temperature you can see was significantly high. These are actually benthic foraminifera. This foraminifera which live in the ocean bottom. Okay, so you can see there are significant variation in the delta 18O by almost 5 per mil. So this ocean was very hot, significantly hot before 35 million years, and this 35 million year onward cooling started and ice formation in the polar region started. There are various climatic and tectonic events are listed on the right side of this plot. I won't go into details of this. Okay, just I want to show you that this, yes, oxygen isotope in the sediments, they responded to various climate phenomena, and we can reconstruct by using oxygen isotope the past temperature as well as this ice volume effect, which I will not discuss today. Okay, so because of this ice formation actually, and due to fractionation, oxygen isotopic composition in the ocean changed. That also we can study using oxygen isotope. Okay, so now I will go to non-traditional isotopes. Okay, so we can use the clamped isotope thermometry for past temperature reconstruction. Okay, so we can reconstruct the sea surface temperature using those foraminifera again, and measure, if you measure the clumped isotope in them, and another entirely different subject, we can study the thermoregulations of dinosaurs using clumped isotopes, and that is a very recent study. Okay, so what is that? I will explain later. Okay, so what is clumped isotope? I will again explain you. If you just consider these calcium carbonate exchange reactions, suppose one calcium carbonate with one carbon 13, another calcium carbonate with oxygen 18, they do exchange reaction and they produce calcium carbonate with one 13C and 18O, and this is the clumped isotope. Okay, so abundance of these purely depends on temperature. Okay, so you do this exchange reaction at lower temperature, there is a probability, high probability that 13C18 bond will form. Okay, and if you go higher temperatures, this 13C18 probability will keep decreasing. Okay, so it is again this definition of this delta 47 clumped is shown here. Okay, so what is the uniqueness of this clumped isotope thermometry? I showed you that this oxygen isotope also we can use to reconstruct the past temperature. For example, we used oxygen isotope to reconstruct the past temperature in the ice cores. Okay, so uniqueness of the clumped isotope is that it is explained in this slide. So suppose if you take some water and precipitate calcium carbonate. Okay, so at a temperature of say 25 degree, if the original water delta 18 is say -7 per mil, we will get a calcium carbonate with delta 18 value of 33.7 per mil. If we take a different water, we will get the different delta 18 in the calcium carbonate. That means the oxygen isotope composition depends on two factors. One is temperature and one is the delta 18 value of the original parent water. In the case of clumped isotopes, it is not the case. Irrespective of what water we take, if we keep the precipitation temperature same, we will get the same delta 47 signature. That is the uniqueness of this clumped thermometry. So we don't bother about the original isotopic composition of the water from which the carbonate precipitates. Okay, so now we can explain, we can use this clumped isotope thermometry to reconstruct the say ocean temperature. As I mentioned in the previous slide where I discussed the oxygen isotope in ocean deep sea sediments, I mentioned that this you cannot use the oxygen isotope thermometry when the ice formation started. Once the ocean ice formation started, because of this ice volume effect, we cannot use oxygen isotope, but you can use clumped isotopes. So we did a small study here from the South China Sea. We recovered this one core from the South China Sea and measured the clumped isotopes in foraminifera, two different types of foraminifera, that is seculifera and rubber. Okay, so I will show you the isotopic records. So here these are the oxygen clump isotopic records in this in the foraminifera in this sediment core. You can see there is a substantial variation of delta 18O. This core actually covered last 28,000 years. That means it covered the Holocene as well as the last glacial maximum period. Okay, so we can see that there is a significant variation in the oxygen isotope from the last glacial maximum to the Holocene. There is almost 1.4 per mil increase in the delta 18O. We can also see that this delta 47, that is the temperature signature, which also increased from say some 0.73 to 0.70. And when we convert this into temperature signal, we can see that this temperature was something about 21 plus minus 2 degrees Celsius during the LGM, and it increased to 28 during the Holocene. Now the confidence comes from this particular Holocene data, because this now the present day sea surface temperature in the region is around this range. Okay, the 28 degree. So that means this clumped isotope is reconstructing the temperature correctly. We compared this actually with the magnesium calcium ratio. So there are magnesium calcium ratio also available from the nearby regions, and we observed that this, yes, there was a decrease in temperature, but the temperature obtained from the clumped isotopes or temperature difference obtained from the clumped isotopes is little bit higher. But of course, these errors are also higher. So more and more studies with more this codes and more samples, of course, will help to better constrain the temperature difference between the Holocene and the LGM. We also showed here the this oxygen isotope data from the North Greenland ice core. You can see there is a substantial of change in the delta 18O, which also 10 degree, but of course the difference in temperature in the polar region will be higher compared to the tropical or subtropical regions. Okay, so next one is that this is the last application of the clumped isotopes. We can use the clumped isotope to estimate the body temperature. Okay, clumped isotopes in the eggshells. Eggshells, you know, they form in the inside the body in the oviparous animals. We can study the tooth enamel also, where calcium carbonates are also there, and estimate the body temperature. Okay, so here I have listed two different groups. One is this middle one is the bird, and the lower one is the reptile. Okay, so we can study the clumped isotopes in the birds and reptiles and estimate their body temperatures. So what is the use of this one? Actually, the importance of this lies in the fact that these animals can be categorized into broadly two categories. One is warm-blooded and another is cold-blooded. For example, we human are warm-blooded animal. Similarly, the mammals, these birds, they are warm-blooded animal or endotherms. So they maintain a fixed body temperature irrespective of the temperature outside. So environment temperature fluctuates. Even if you go to polar regions, our temperature will remain 60 degree. It will not drop. But if those reptiles, for example, these lizards, tortoises, crocodiles, snakes, they cannot maintain their body temperature. Okay, so their body temperature will fall with the outside temperature if outside temperature drops. Okay, so now what is the use of this one? So now actually dinosaurs being reptiles, they are initially thought to be cold-blooded. So this is actually a very important subject of evolutionary biology. Okay, so dinosaurs initially thought they are cold-blooded, but there are many observations. For example, their paleogeographic distribution that they found in coregions as well. Okay, so and their this growth rate analysis, they suggested that probably some of the species, if not all, were not probably cold-blooded, probably warm-blooded. Okay, so we did this clumped isotope measurements in the eggshells of dinosaurs. Okay, so we recovered some eggshells from western part of India, Gujarat and Madhya Pradesh. Okay, and did some analysis. Okay, so important thing is that the dinosaurs, they got extinct 65 million years before. So how do you ensure that this the eggshell, whatever you get, they are well preserved? Because for isotopic study, you need well preserved samples. So there are various indirect ways to ensure that whether they are well preserved. One test I have shown on the right side. This we measured the eggshell, delta 13C, delta 18O, as well as in the horst rock, delta 13C and delta 18, and we found that there is a significant difference. If there are homogenization or a significant alteration, we expect not much difference in the delta 30C, delta 18O. Similarly, we did some other analysis. I did not show those things. We did this secondary electron microscope imaging, and there we observed whether this original shell structure was preserved or not. So we only analyzed those samples where we found this shell structure were preserved. Okay, so now this is the results. So this results show, this plot shows the probability distribution of body temperatures of reptiles, dinosaurs and birds. Bird is shown by red, dinosaur by the middle one, intermediate one, and this blue one is the reptiles. You can see that this reptiles body temperature is somewhere between 20 and 25 degree. Average is somewhere 23 degree. It is much less compared to the birds. Birds body temperature is something about 40 to 45. So there is a this difference between the gap. There is a very big gap between the body temperature between these two kinds of animals. So top panel shows the box and whisker plots for these three kind of categories. There are two things, important things we can note down from here, that this dinosaurs body temperatures intermediate between these two groups, one thing, and second thing is that this spread, this temperature spread in the dinosaur is much bigger compared to the other two groups. Okay, so these are the two important informations that suggest that these dinosaurs are probably, you cannot categorize directly to ectothermic or endothermic, or some of the species probably maintain the ectothermic metabolism and some of them maintain the endothermic metabolism. Okay, So that these are the inferences we can get. And our conclusion from this study was that this probably the dinosaurs had intermediate thermoregulations. Their body temperature, depending on the requirement, they could elevate or they could maintain their body. They could maintain their body temperature similar to the environmental temperatures. Okay, so here is the plot where this body temperature is scaled with the body mass. Okay, so the left side is the body temperature, y-axis, and x-axis is the log of body mass. So actually, it is. I want to compare this reptiles, birds, and dinosaurs on a scale where the body temperature is found to increase with the body mass for the reptiles. Okay, so reptiles actually, if it is small species, then it will have similar to the environment. Say environment temperature is 25 degree. Reptiles, small reptiles will have body temperature 25 degree. Okay, but as their size increases, their body temperature increases. That is simply because of thermal inertia. Okay, so higher mass species that take time to lose the heat or they take time to gain the heat. Okay, so I also plotted this dinosaurs here. So you can see that some of the low body mass dinosaur species have body temperature similar to the environment, and some of the low body mass species have body temperatures much elevated and similar to these birds or mammals. Okay, and some of these giant species, big dinosaur species, you can see on the right side, their body temperatures are significantly lower compared to this model plots. Okay, so that means dinosaurs, they did not uniquely follow low body temperature or high body temperature. Okay, so they are probably either intermediate or their body temperature, their mechanisms to elevate their body temperature compared to the environment. So that is the main conclusion, and I have compared many recent studies. Actually, 3-4 recent studies are done on the dinosaurs using clamped isotopes, and I have reported that also in this plot. Okay, that's all about this today's lecture. So I will summarize what I discussed. The ice cores, sediments, foraminifera and speleothems are important paleoclimate archives, and stable isotopes in them can be used for reconstructing past climatic conditions. Okay, oxygen isotopic composition of ice cores record past temperature variation. Oxygen isotopic composition in cave carbonates can be used to decipher past temperature and rainfall. Okay, so carbonate clamped isotope thermometry has potentials to directly estimate the sea surface temperature using foraminifera and infer the thermoregulations or by inferring the body temperatures in dinosaurs using fossil eggshells. So I will stop here. I will acknowledge, I will thank my supervisors and collaborators who are part of these works, whatever reported here. So they are listed here, including my PhD supervisor, late Professor Ramesh. Okay. Thank you all for your attention. This plate is over Dr. Vinita Patel now.
Hello. Yeah,
yes, Vinita. So,
thank you, Amjad. Very, very, very interesting talk. I would like Linjo to take over, please, for some questions and queries.
Oh, yeah.
Interesting ones that have been raised by our listeners.
Okay, so this,
Amjad, there are a few questions. The first one is that why to use both CO2 isotopes and oxygenating isotopes for ice cores, whereas CO2 studies are also showing increasing and decreasing in temperatures.
Just let me clarify this. This CO2 actually is a concentration. In the plot where I showed this, let me go to that plot. Yeah, this is the actually CO2 concentration and temperature. This temperature is reconstructed using delta 18O in the ice core, and CO2 is reconstructed based on the concentration observed in the bubble trap in the ice cores. So there are two different things. I hope it is clear. So this is not CO2 isotope and oxygen isotopes. CO2 isotope means does nothing. So either carbon isotope in CO2 or oxygen isotope in CO2.
Okay, that was a question from Vamshi Sandeep. I hope it is clear now. There is one more question by Abhilash Mishra. Can we get details about the sea level fall or rise from the paleomonsoon studies using oxygen or carbon isotopes? Amjad.
Yes, using oxygen isotopes, we can get information of the sea level rise as well, but that I did not show here. Okay, so yes, we can do that.
All right, thank you, Amjad. There is another question by Bilal Sunu. Is beryllium-10 and aluminum-26 is helpful for paleoclimatic reconstruction? I think it's something different from what you have talked so far. So maybe if you can attend, that would be nice.
Yeah, actually we can do that. So those are actually entirely different proxies. Beryllium-10 and aluminum-26, actually they are cosmogenic radionuclides. Yes, you can measure them even in sediments also, but mostly people measure them in they mostly measure in this glacier retreat and all these things to study them. So yes, they can be used.
Okay.
But mostly they are used for dating also. Okay.
That's nice. Thank you. Amjad, there is one more question that is Snigdha Gathak had asked, any correlation with Maula Cave, Meghalaya?
I can't answer that question at the moment. I heard about some paleoclimate record from this Meghalaya caves, but I didn't see those records so far. Sorry, I can't answer that question.
Okay, so there is a few more questions by one Miss Gupta. She has asked, does the global warming continues even if we limit the production of greenhouse gases, as the lifetime of most of the greenhouse gases are high in the atmosphere?
Actually, that's what I showed in one of the slides in the very beginning. Yes, these slides actually showed stop the greenhouse gas emission, particularly CO2. Still, global warming will continue for some time, for a significant, for some decades. Yes, it will not stop immediately.
Okay, that's nice. Thank you. Then one question by Ms. Sarkar. Sir, one question I want to ask, how the scientist had selected the Epica Dome C for the dating of ice core? What were those characteristics for selecting the distinct one?
Yes, actually it is a good question. You have to be there are actually many ways to select where to collect the ice core samples. Where we can go the maximum, we can get this long core, as well as we can go back in time. Yes, there are many criteria. At this moment I don't recall all these criteria, but yes, I can tell you that there are criteria to select the ice core.
Okay, and one more question. Can you please explain how Meghalayan age was deduced by Speleothem isotopic study?
Okay, so again I'm sorry, I cannot answer properly this question. Because I heard that about the Meghalayan Speleothem study, but I did not go in details. Okay.
And there is a few more questions about comment on the influence of enzymes on the calcification of eggshells and temperature reconstruction.
Can you repeat? Sorry.
That is about comment on the influence of the enzymes on the calcification of eggshells and temperature reconstruction.
Okay, so yes, that is an important question. This influence of these enzymes was in this delta 47 clamped isotope was observed not significant. We observed that there is no effect of enzyme on this clamped isotope that we checked with the modern eggshells. Okay, so what we did is we measured many of these modern eggshells, and we found that this whatever temperature we got from the delta 47, it is same as their body temperatures. and that gave the confidence that yes, we can use the clamped isotope. So this influence of these enzymes, if there, it is not significant at all at our measurement limit.
Okay, thank you, Amjad. One more question from Abhilash Mishra. Does changes in the isotopic ratios can affect majorly fossil preservation, be it minor or major change in ratios?
Sorry, I didn't get the question. Can you repeat it again?
The changes in the isotopic ratios, whether it can affect majorly fossil preservation, be it minor or major change in ratios.
Still, this question is not very clear to me. What he wanted to ask. Can I read those questions?
Yes, that is on the chat box. It's at 257.
$249.
No, it must be later then because I have a wrong.
Then the next question is 301. This Snigdha.
Can you check for the Abhilash Mishra question? I think Abhilash is present here. Maybe you can ask. Unmute and ask.
Yeah. Yes.
Okay, I don't see that.
Oh, yeah, I got the question. Yes.
Okay.
Does changes in the isotopic ratios can affect majorly fossils preservation, be it minor or major change in ratios?
It's about the preservation of the fossil. Whether
of course. This maybe probably he wanted to ask me that whether this preservation will influence the isotopic ratios. If that is the case, yes, preservation will affect the isotopic ratios, and we have to ensure that this sample must preserve its original isotopic signatures before applying for any kind of paleoclimatic or body temperature reconstructions. We use multiple ways to ensure that. One is we check the oxygen and carbon isotopic records in the sample as well as surrounding rocks. One thing. Second thing we did is we did this scanning electron microscopy on the samples and checked whether those samples preserve their original shell structure or not. So these are the two things. Another thing we also did is magnesium oxide concentration in the sample as well as in the host rock. We checked that and we found that they are significantly different. So if there is a significant alteration, of course, we would observe the similar isotopic composition as well as blurred or deformed SEM images and magnesium oxide concentrations. So these are the three things we did. I hope I answered his question.
Okay. Amjad,
okay, so next question is.
Yeah, please.
Yeah, I can read the next question.
Yes.
Next question is by Pritam Sharma. Wonderful presentation, especially the last on the application of clamped isotopes. Thank you. I have a query that why all these multiproxies are not capturing the same trends in terms of temperature or precipitation for some prominent short events. Example, let's take example of reconstructing the Little Ice Age. Yes, it is an interesting question. Why these different proxies, they don't record the similar things. So first thing is that if it is a regional phenomena or global phenomena, you should observe all these isotopic proxy records, unless there is some local changes. If some local changes or something happened, that you have to ensure that this sample should not be affected by some local events, local phenomena, for example, some anthropogenic activities. So those things could be the reason for differences in the proxy records. Otherwise, you should see similar observation or similar variation in all these proxy records if it is a global or regional phenomena. Okay, so next next question. Manoj MC, when you are using fossilized eggshells, particularly the dinosaur eggshell, how the recrystallization influence the isotopic data? Yes, that's what actually we discuss. If recrystallization takes place, then there will be homogenization of isotopes. Okay, so if recrystallization takes place, then this host rock and the sample will not have very different isotopic composition. This is one thing. Second thing is that if recrystallization takes place, you can see that in the SEM images. Okay. So yes, and for this, particularly for the carbonates, for this recrystallization takes place, the temperature should be high, say 250 degree or above. That is the people observed that this significant recrystallization takes place when these samples encounter temperature 250 degrees Celsius or higher. But it is very unlikely that in the last 65,000 years, this earth crust, any of the parts of the earth crust experience such type of high temperature unless some volcanic activity took place in particular region. Okay, so if there is some recrystallization, yes, we can see that one, we can test that one. Next question by Anupam. Is this possible that recrystallization do not alter the eggshell structure? No, it will alter the eggshell structure. But even if it does not alter the eggshell structure, there will be many other things which we should observe. This fluid inclusion, local fluid inclusion, there is a possibility that fluid will include fluid will enter into the calcium carbonate we measured, and that will change the isotopic signatures. So that also we can check. Okay. And what is host rock from where these shells were recovered? The host rocks actually, this is the rock where these samples reside, and these samples were recovered from the western part of India. Some samples from Gujarat and some from Madhya Pradesh. Next question.
Hello.
Can you use clammed isotope for? Yeah.
Hello, Amjad. Because we are running it's already 10 minutes.
Sorry.
Ago. Can we take all these questions? We'll send it to you. You can please answer them on the YouTube platform or wherever, or maybe our website, which will be launched. But these questions will be answered, I'm very, very sure. So because people are leaving and, it won't be very good to just to continue. So Linto, can you please deliver a vote of thanks? Thank you, Amjad. It was really great, interesting. I'm already getting so many messages here saying that the talk was very interesting, and they're congratulating all of you. I also congratulate you on behalf of AOQR. Over to you, Linto, please.
Thank you, ma'am. So let me go to my duty of proposing vote of thanks. A very good afternoon to one and all present here. After listening to the interesting talk by Amjad Hussain Lashkar, I'm sure that the webinar today was a fruitful and knowledgeable experience for all the participants. We have already seen the number of questions that has come, and I'm sure, Amjad, you have generated a lot of interest among the participants. That is truly a great success for your talk. So let me express our sincere gratitude to Dr. Amjad Hussain Lashkar, who has graciously accepted our invitation to give the first lecture of the AOQR webinar series. Thank you, Amjad. Thank you for accepting our invitation. I want to thank all the people who made this event a success. The president of AOQR, Dr. Vandana Prasad, the founder members, Vice President Dr. Pradeep Srivastava, Secretary Dr. Binita Fatiyal, Treasurer Dr. Santosh K. Shah, and other founding members, Dr. Parth Chauhan, Dr. Rahul Mohan, Dr. Vandana Chowdhury, Professor Sadish Sangode, Dr. Ragesh Chandra, Dr. K. Anbarashu, for their constant support and encouragement. I would like to express our gratitude to our honorary members, Professor A.K. Singhvi, Professor Vishwas Kale, Professor Hema Achudan, Professor L.S. Chamyal, for showing us the path in bringing up this association and various programs under its banner. I also wish to say thanks to the quaternary group of BSIP, our ECR group, Dr. Sendil Kumar Sadashivam, who was behind all the designing part of the newsletter and also the flyers of the webinar. Dr. Manoj, Dr. Ayush Srivastava, who gave the idea of coming up with the webinar, Mr. Akash Srinivas, Jyoti Srivastava, Dr. Trina Bose for their constant support. Now comes the most important group of the program, our distinguished participants, many of whom are faculty, research scholars, students, and other quaternary science enthusiasts. It's your interest and cooperation made this program possible today, and that will take forward in the upcoming days. Please keep all Mondays of September and October marked as we have more interesting lectures coming by. So thank you, everyone. I also express our sincere gratitude to the principal of Christ College Autonomous, Kerala, Dr. Jolie Andrews, the IT team of the Institute for extending the facilities for live streaming today's lecture in response to our last minute request. There was an interesting query from a student participant about how to get involved in the activities of AOQR. And I must say that you have a number of avenues to get associated with the association, primarily through our ECR team, and also via our newsletter by sending us your interesting observations about quaternary sciences in India and so on. So please tell us how you could help us. And we are happy to welcome you on board to make it available to our for the better reach of our quaternary researchers fraternity. So with these words, I conclude. Thank you once again. And ma'am, with all your permission, may I?
Yeah, please. And please, everybody, a request to please fill in the feedback forms so that we can improve. For students, it is like an attendance, but from all of you, it would be like, where we have missed something so that we can improve in a next webinar. So thank you all again. Thank you, Linto. Thank you, Amjad and Manoj. Thanks, everybody.
Thank you.
Namaskar.
Thank you.